Hi all, I am Dr. Sureka Samundi, Assistant Professor, Department of Aeronautical Engineering, Bharat Institute of Higher Education and Research. So in my previous video, we have seen about the basic concepts of aircraft stability and control. So today we are going to see about the criteria for the longitudinal static stability. Yes. So before getting into the criteria, it is mandatory for us to know about the parameters which are literally involved in the stability and control. And moment is one of the important parameters. So moment, we know that moment is the force into perpendicular distance. And take a look into this figure. So F1 and F2. So F1 is the net force which is acting in the downward direction. F2 is the net force which is acting in the upward direction. And F1 and the F2 are the pressure forces which are acting on the upper surface of the FOL and the lower surface of the FOL respectively. And F1 and F2, say for example, if F1 and F2 are equal to each other. And how about the moment established by these forces? Yes, the moment established by these forces is pure couple. So, like we know, when it is pure couple, then the moment about any point along the line are equal to each other. So, the moment about the leading edge is equal to the moment about the water cord point. So, that's the reason we have equated the momentum in this equation. So, moment about the aerodynamic center is equal to the moment about the water cord point, which is equal to the moment about any point. Yes, and L is equal to 0. What do you mean by that? So lift is equal to 0. So if F1 and F2 are equal to each other, then it actually means that lift is equal to 0. So in order to obtain lift, F2 should be greater than F1. Yeah. And what about the aerodynamic center? The lift, drag, and the moment varies with respect to angle of attack. So as angle of attack changes, these values will change. But there is a particular point about which the moment is independent of that of the angle of attack. And that corresponding point is called as the aerodynamic center. And CMAC represents the coefficient of moment about the aerodynamic center. So as far as the stability and control is concerned, the aerodynamic center plays a vital part. Yes. So the next one is the moment about the center of gravity. So like the point at which the net weight acts is called as the center of gravity. Look at this figure. So our intention is to calculate the moment about the center of gravity. So we all know like all the forces and the moment acting in the airplane contribute towards the moment about the center of gravity. The lift, drag, and the moment of the wing, the lift of the tail, the thrust, and the aerodynamic forces, and the moments on the fuselage and the nacelle. And since the weight is acting at the center of gravity, the perpendicular distance is 0, and hence the contribution of the weight towards the moment about the center of gravity is nil. Yeah. And a trimmed airplane. So, like a trimmed airplane is nothing but the airplane in equilibrium condition in pitch. So, say for example, if the airplane is able to maintain an equilibrium condition at certain angle of attack, then you call that airplane as the trimmed airplane, and that corresponding angle of attack is trimmed angle of attack. So, if an airplane is in equilibrium condition, then the moment about the center of gravity is 0. If the moment about the center of gravity is 0, then obviously the coefficient of moment about the center of gravity is also 0. And the coefficient of moment about the center of gravity is defined as the moment about the center of gravity to the dynamic pressure into S area into the chord. And the second parameter is the absolute angle of attack. So far you have studied about the geometric angle of attack. So here we are just introducing a new term called as the absolute angle of attack. Yes, why absolute angle of attack? Yes, so just look at this airfoil. What type of airfoil is this? So since there is a value of camber, you call this as cambered airfoil. And Yeah. What is the geometric angle of attack? So it is the angle between the relative wind direction and the chord line. And you see, so now just observe this graph. So this is the lift curve. Lift curve is the curve between the lift and the angle of attack. Since it is the lift curve for a cambered airfoil, the coefficient of lift is 0 at a negative angle of attack. So somewhere here, the value of CL is 0, and at that point is termed as the zero lift angle of attack. Yes. So what is a zero lift line? So you by setting the airfoil at zero lift condition, when you draw a line through the trailing edge and parallel to the relative wind direction, then that corresponding line is called as the zero lift line. And the angle between the chord line and the zero lift line is nothing but the zero lift angle of attack. Yes. So now look at this figure. Alpha is the geometric angle of attack. Alpha L naught, zero lift angle of attack. And alpha A, which is nothing but the absolute angle of attack. So the absolute angle of attack is the summation of the geometric angle of attack and the zero lift angle of attack. But why absolute angle of attack? Why not alpha A? So if at all, if you are dealing with symmetric angle of attack, then there is no issue. The value of zero lift angle of attack is actually 0. So as far as your symmetric angle of attack is concerned. But when we are dealing with cambered airfoil, then the zero lift angle of attack comes into picture. This value changes with respect to the camber of the airfoil. So for designers, they felt inconvenient to consider the different camber. So that is the reason why they had incorporated the absolute angle of attack into account. So as far as your stability and control is concerned, the absolute angle of attack is used in layoff the geometric angle of attack. When you observe these two figures are identical to each other. The plot are identical to each other. But the only difference is it is with respect to geometric angle of attack, whereas the right hand side grid plot is with respect to the absolute angle of attack. So the absolute angle of attack is the summation of the geometric angle of attack and the zero lift angle of attack. So this plot is it does not depends on the camber. So the designers felt it convenient for them to study the aircraft stability and control. So that's the reason why they had used the absolute angle of attack. Yes, so here comes the criteria for the longitudinal static stability. Let us consider a rigid airplane. We are just testing it in a wind tunnel or free flight test condition. And this plot is obtained out of a test. There is no any reason behind getting this plot. The plane has undergone some test, and CMCG, when we are plotting CMCG versus absolute angle of attack, this plot is obtained. And you see, at along the x-axis, there is a point. So along the x-axis, the coefficient of moment is 0. So here at a point of alpha E, which is trimmed angle of attack, E for equilibrium. So alpha E is the trimmed angle of attack. So at a trimmed angle of attack, the coefficient of moment is 0. About the center of gravity is actually 0. Similarly, along the y-axis, alpha A should be equal to 0. So here at the point of CM naught, the alpha A is equal to 0. What does this naught indicate? So at alpha A, when alpha A is equal to 0, what happens to the lift? Lift is equal to 0. Yes, so look into this figure. So at 0 absolute angle, CL is equal to 0. So whereas here at some when we just compare this one with the CMCG versus alpha plot, this zero lift angle of attack will play an important role. That's the reason why they have chosen absolute angle of attack instead of the geometric angle of attack. So So when lift is equal to, when alpha A is equal to 0, then lift is equal to 0. So when lift is equal to 0, you represent CMCG as CM naught. And CM naught is in the positive. So CM naught is positive, actually it is in the positive y direction. And how about the slope? As the alpha A increases, the CMCG decreases. So the slope is negative. So if we are plotting CMCG versus alpha A, then that corresponding curve is called as the moment curve. So if they mention its moment curve, it is understood that it is a plot between CMCG versus absolute angle of attack. Yes. So now we are just going to examine this graph. So the first aircraft is in equilibrium condition. So since it is flying in equilibrium condition, the angle of attack mentioned is alpha E, which is trimmed angle of attack. So at trimmed angle of attack, the aircraft is managed to move in the equilibrium condition. So that's the reason why CMCG is termed as 0. And let us consider, because of some disturbance, the aircraft is pitched upwards. So when it is pitched upwards, it actually means the angle of attack, the absolute angle of attack during this condition is actually greater than the trimmed angle of attack. Now go to the plot. So look at this. So when the angle of attack is greater than the trimmed angle of attack, then how about your CMCG? It falls in the negative y direction. So till alpha E, it is in the positive y direction. So beyond alpha E, it is in the negative y direction. So when alpha A is greater than alpha E, then CMCG is negative. So by the universally accepted sign convention, when coefficient of moment is negative, then the moment is in the counterclockwise direction. So now see, when the moment is in the counterclockwise direction, what happens to the aircraft? The aircraft is tending to move towards the original position. Now come to the third one. So when you just move to the third figure, so the craft is disturbed, and because of the disturbance, the craft is pitched in the downward direction. So when it is pitched in the downward direction, then the absolute angle of attack will be less than the trimmed angle of attack, somewhere less than. So when it is less than the trimmed angle of attack, what happens to CM naught? CMCG, the CMCG in the positive y direction. So when CMCG is positive, then by universal sign convention, the coefficient of moment is in the clockwise direction. So now look at this figure. So when it is moving in the clockwise direction, it actually tends the aircraft to move towards the original equilibrium condition. So which means that it tends to move towards the stability. So understood? So just to recollect the previous video. So we have studied about the static stability, right? When the aircraft tend to move towards the equilibrium condition, then you call that a static stable condition. So even in the second and the third figure, so in both the cases, the aircraft is tending to move towards the equilibrium condition. So by doing so, the aircraft is planning to go to the equilibrium position. Right. So now let us go to the second. Let us consider, like, this plot is obtained out of our wind tunnel test. So if it is actually due to the wind tunnel test condition, then how about CM naught, the coefficient of moment at zero lift condition? It is actually negative. And how about the moment curve slope? So as the alpha A increases, your CMCG is also increasing. So the moment curve slope is positive. So now consider the first diagram. So when you just observe the first graph, it is the CMCG is equal to 0, which means that it is moving in the equilibrium condition at the trimmed angle of attack. And now due to some disturbance, the craft is pitched upwards. So when it is pitched upwards, what happened to your alpha A? So your angle of attack, absolute angle of attack will be greater than the trimmed angle of attack. So go to the plot when alpha A is actually greater than trimmed angle of attack. How about your CMCG? Your CMCG is positive. So when CMCG is positive, how about the sign convention? So it tend to move in the clockwise direction. So when it tend to move in the clockwise direction, the aircraft is again moving somewhere away from the equilibrium condition. It is not coming back to the equilibrium condition. It moves somewhere away from the equilibrium condition. Yes. Now coming to the third one, look at the third figure. So here, because of some disturbance, the craft is pitched downwards. So when it is pitched downwards, then how about your absolute angle of attack? It is less than the trimmed angle of attack. So now go to the plot. If it is less than the trimmed angle of attack, then how about your CMCG? The CMCG is in the negative y-axis. So when it is negative, then how about the sign convention? It is counterclockwise direction. So when it is in the counterclockwise direction, look at this figure. So it is tending to move the aircraft somewhere away from the equilibrium condition. So in this case, when it is pitched upwards by disturbance or pitched downward by disturbance, in both the cases, the craft is tending to move somewhere away from the equilibrium condition. So which means that it is completely unstable. So what is that you understood from the two observations? Like, so from the first case, you observed that if the plot is something like this, then the aircraft is tending to come back to the equilibrium condition. And if the plot obtained is something like this, then it is making the aircraft away from the equilibrium condition. That is unstable condition. So how about the criteria, the necessary conditions for longitudinal static stability? The first one is Cm naught should be positive and the slope dCmCG by d alpha A must be negative. It should be the lift curve slope, moment curve slope should be negative. And how about your alpha E? Yes. So if you need a balanced condition, then your alpha E should range between the maximum angle of attack and the minimum angle of attack. So like it should be with respect to the velocity. So at stall velocity, what about your angle of attack? At maximum angle of attack, your CL at its maximum. So when CL is maximum, then your velocity reaches the stall velocity. So at the stall velocity, the angle of attack is maximum. When your velocity is maximum, then the angle of attack is small. So like your trimmed angle of attack plays an important role. You have to ensure that it falls within the flight range of angle of attack in order to get a balanced condition. Yes. So that is what about the criteria. And now coming to the, what is the necessity for the horizontal stabilizer? In the previous case, you understood like how to maintain the longitudinal static stability. When it is capable for a pilot to maintain the longitudinal static stability just with the wings, then what is the necessary for a horizontal stabilizer? What is the necessary for an elevator? Yes. So you see, like this is where the design comes into picture, and this is where the Wright brothers proved themselves as genius. Yes. So, like, as far as your cambered airfoil, so when you just go through the airfoil data of any cambered airfoil, the coefficient of momentum about the aerodynamic center will be negative. And you just keep that in mind. So now for a wing alone condition, there is no any horizontal stabilizer at all. So you're just planning to maintain the longitudinal static stability just with the wings. So for a wing alone condition, when the wing is set at a zero lift condition, you know that CM AC is equal to CMCG from the previous discussions. And when it is at zero lift, then CmCg is equal to Cm naught. So which means that Cm naught is equal to coefficient of moment above the aerodynamic center. So for a cambered airfoil, from the airfoil data, what we know, CmAc is negative. So when CmAc is negative, it is obvious Cm naught is also negative. How about when Cm naught is negative? What about your stability? Yes. So necessary condition is your Cm naught should be positive for a stable flight condition. So as far as your positive cambered airfoil is concerned, your Cm naught is negative. So what it actually means? It means that it is imbalanced. It is not stable at all. So this is where the horizontal stabilizer comes into picture. So as far as your camber, your symmetrical airfoil is concerned, the pilot can manage just with the wing alone. Whereas when the positive cambered comes into picture, then the horizontal stabilizer plays its role. Yes. So now you see, the first one is the conventional wingtail contribution, and the second one is the Canada type combination. So as far as your why it is conventional type of combination and why it is canard, if the tail is placed behind the wing, then it is conventional type combination. When it is when the tail is placed ahead of the wing, then it is canard type combination. Yes. When the tail is placed behind the wing, and when it is deflected in the downward direction, it produces the negative lift. So when the negative lift is generated, it actually moves in the clockwise direction. So when this moment, because of this negative lift, is strong enough to overcome the negative uh, uh, moment about the aerodynamic center, then you can get the positive value of Cm naught by the combination of the tail. See, look at this. So here it is in the negative direction. So see, your center of gravity will be somewhere ahead of the tail. So it should actually move in the clockwise direction. So when it is moving in the clockwise direction, and when it is strong enough to overcome the moment about the aerodynamic center, which is actually negative, then the combination of the wing and the tail, it can get the positive value of Cm naught. Similarly, in case of the Canada wing-tail combination, when the tail is deflected in the upward direction, it creates the positive lift. And when the positive lift is generated, so you see, it should move in the clockwise direction, and when this moment is actually strong enough to overcome the coefficient of moment about the aerodynamic center, then the combination of this moment with the wing, it is obvious they'll get the positive value of Cm naught. So positive value of Cm naught is one of the important criteria for the longitudinal static stability. And this is the reason why the horizontal stabilizer plays an important role. And you see, the canard wing-tail combination is actually a failure one. That is because this tail actually interrupted the flow towards the wing. So since it is interrupting the planned lift, the designed lift cannot be obtained by this configuration, and that is the reason why the canard wing tail contribution combination is an failure. And this is the right flyer. See, so orbital is here, and can you see the horizontal stabilizer? The Wright brothers, they used to call the horizontal stabilizer as rudders. They used to term this as rudder. They just located the stabilizer ahead of the wing. So this is your canard wing tail combination. So now, so because of this, they felt some disturbance. So what they did is they just tried to increase the length of the machine. So by extending this length, they just flow. But after so many trials, so this is Rifler 1903. So after so many trials, Orwell found that this horizontal stabilizer ahead of the wing is one of the important drawbacks. And this in 1910, they just placed that behind the wing. So even those people know, those personalities, they have analyzed and observed the drawback of the canard wingtail configuration. So that's the reason why in 1910 they in their model B, they just located the horizontal stabilizer behind the wing. Yes, so of course they are genius, right? Yes. Yes, guys. So as far as this video is concerned, we have studied about the qualitative perspective of the longitudinal static stability. Yes, but it is mandatory for us to know the quantitative parameters, right? Yeah. So what is the length? How long the tail should be placed away from the wing? And what about the dimensions of the tail? And we just mentioned that the trimmed angle of attack should fall within the range of the maximum and the minimum angle of attack. But what is the range? What is the desired value of trimmed angle of attack? So these are all are going to determine the quantitative parameters. So it is mandatory for us to understand the uh, quantitative discussion. Yes. So we'll just discuss that in our next video. So hope you guys understood about the criteria of the static longitudinal stability. So we'll just discuss the rest in the next session. Thank you, guys. Thank you.